Hello everybody, this is Víctor Álvarez, and today I'm going to talk about how Julia has allowed our team to develop a new collection of algorithms regarding Julia sets and rational maps from a dynamical perspective. These algorithms can be found in the Lyapunov cycle detector repository on GitHub, and they provide methods to study and visualize the basins of attraction of a complex rational map, avoiding some computational problems that often appear in software devoted to numerical analysis, such as overflows or mathematical indeterminations. But first of all, here's a bit of context without getting into too much technical detail. Let's see the following image. In this graphic, the points in black are those that when we iterate them under a rational map, in this case the polynomial c squared minus 0.4 plus 0.6i, the iteration goes to infinity, while in case of the white points, the iteration converges to a n-cycle, or it does not converge at all. The white points are what we call the Julia set of this polynomial, or more precisely, the Julia set is the boundary of this white region. We can zoom in this graphic to appreciate the complex fractal pattern it presents. Here are a few more examples of these Julia sets of different rational maps. We can also zoom in these graphics to have a look at the surprising beauty that arises in the behavior of these polynomials under iteration. We see that Julia sets may present both beautiful and intricate fractal patterns, which often make them not easy to study mathematical objects. Also, without getting too much technical, we observe that every pattern we can see in a small region of the graph is reproduced with different sizes in many other regions. While Julia sets might seem a bit abstract at first, the fractal structure they present allow us to study and better explain many phenomena that occur in nature, as you can see in these two examples. They actually appear frequently in a lot of problems related to complex dynamics and discrete time dynamical systems. However, for a certain rational map, we may also be interested in distinguishing the regions of the complex plane where the iteration converges to one specific n-cycle or another. These regions in the complex plane are what we call basins of attraction, because every 2 points that are in the same basin will eventually converge to the same n-cycle when we iterate them through a rational map. In this example, we can see the basins of attraction of the polynomial c to the fifth minus 1 under the iteration of Newton's method. So we are iterating the rational map induced by Newton's method applied to this polynomial. The graphic on the left corresponds to a neighborhood of the origin in the complex plane, while the one on the right represents a neighborhood of the infinity point. In both of them, the colors represent each basin of attraction, and each one corresponds to one of the 5 roots of the polynomial c to the fifth minus 1. As you can see, below the graphics is the precise function that was used to compute them. We think that the rich ecosystem for scientific computing and parallel programming Julia language provides is the ideal place to implement our algorithms, since this kind of calculations can often have a large computational cost. In particular, the algorithms we have implemented in Julia allow us to compute graphics in which we can visualize the basins of attraction of a rational map, as we have seen earlier. Also, they are a tool with which we can study some dynamical properties of the induced dynamical system. Let's summarize the main ideas behind our algorithms. First, we shall take a rectangular grid of points representing some region in the complex plane. Our goal is to determine which basin of attraction each point belongs to. In order to do this, we use topological concepts that allow us to avoid overflows and other numerical problems that one might encounter with this kind of algorithms. Thanks to this topological approach, one can also work with a neighborhood of the infinity point, as we have seen before. Our algorithm computes this function in order to work, called a Lyapunov function. It is constant and non-negative in each basin of attraction, This way, if we evaluate this Lyapunov function in 2 points and the two resulting values are equal, we know that the 2 points will belong to the same basin. These constants measure the attractive power of each basin of attraction. The smaller is the constant, the more attractive is the basin. Also, these constants are closely related to Lyapunov exponents, a very useful concept often used to study the local stability in continuous dynamical systems. In fact, the logarithms of the constants we are computing are the Lyapunov exponents of the considered rational map. As we can see in this fragment of code, most of the calculations needed to compute our Lyapunov function are sums and products, and we know Julia is extremely fast in performing that kind of calculations. Also, as some of you might have noticed, the grid of points we are working with is embarrassingly parallelizable, so we can use some of Julia's built-in options for parallel programming. In our case, as you can see on the left, we have used multi-threading, reducing considerably the execution time of the algorithms. In our work, we apply these techniques and algorithms to study some established and very well-known iterative processes such as Newton's method. Here is an example of the basins of attraction induced by this method applied to the following cubic polynomial. We can see here that the black regions correspond to the basin of attraction of an attracting 3 cycle, represented with blue segments, both in a neighborhood of the origin on the left and the infinity point on the right. Observe that the boundary of these basins of attraction is in fact the Julia set of the induced rational map. And here we can see its complex fractal structure. In these last 2 graphics, the number of iterations needed to converge is represented on the right. Here we can appreciate the local instability of the basin of the 3 cycle. In this case, the chaotic behavior of the number of iterations arise due to the 3 cycle having very little attractive power. And that is all I have for you today. If you are interested in these algorithms, you can check the lcd.jl repository on GitHub, where you will find not only all the code, but also multiple examples and a user guide that explains every functionality that the code has, so you can easily use every single part of the code. Thank you all for your time and have a great day.